ฮัลโหลโอเค
จอมปล่อยเลยก็ได้เดี๋ยวเราเปลี่ยนแบ็คกราวด์นะอันนี้นะแล้วก็ full screen โอเคต้องปิดไฟอย่างนี้ไหมหรือไม่ต้องกดยังไลน์ Okay, I think we have started. Good morning, distinguished speakers, lecturers, students. My name is Valodom Vilapan, College of Computing, Prince of Songkla University. Today, I'm glad to welcome you to the first consortium of ASEAN research on how will computing change. Before we start, may I have an honor of Professor, the chief of the consortium. Please proceed on the stage.
Okay. Good morning, everyone. Morning. Good morning. I think we are from different places, and you may have a question why we are here, right? So let me explain. Actually, I met Aziz, the dean of the College of Computing, maybe several years ago, and we would like. He has many friends. I also have many friends, and we talk about the research. And we know that in doing research, we need friends, especially in different fields. That's why we would like to exchange friends. Okay, as this has his human network, I also have my human network, and now we have many. I invite friends. I mean research friends from north of Thailand, Mephaluang, and in the northeastern from Khon Kaen University, and in Bangkok, and in the middle north. So they also have human networks, and we exchange. You see that Dr. Dharani invite Andrew from UK, very far away. You are most far from here. And I have a friend from University of Malaya. She's saying he will give a talk as the first speaker. So that's why we are here. So this is the objective. I don't care the title. Okay. So please exchange. First, we introduce our own research as your introduction. And then after that, during the lunch and the break, please exchange your name card or conversation. Okay. So without further ado, I would like to open our seminar, and please enjoy the seminar. Thank you very much.
Thank you, Professor Kosin. Next, as we are hosts of this consortium, may I invite Assistant Dr. Professor Aziz Nanta Amonpong, the Dean of College Computing. Please welcome.
Thank you, Professor Dr. Kosin Chamdongthai, and Assistant Professor Valodom Vilapan for introduce me. And on behalf of the College of Computing and Prince of Songkla University, I would to welcome all to the College of Computing and for welcome to Phuket. I think this is a good opportunity because it seems that we just opened the new Phuket you all. And you are, I think, is the first group to visit us for now after the COVID-19. I just have to say that today I think that as Professor said, the title is not important, but it is a starting point for us to connect together, and we can make extend our connection in the future. And I hope that after today we can do something together, and we should have the second consortium in future. Place like Mat Pha Luang or something. So is there some other or in Bangkok, something like that. And actually today I have something to tell you. Actually, today it should have some more people than it, because today in the big we have a big conference in Hua Hin for the ECCICon 2022, and some of our ECI committee, I think some told me that actually he interested to come here, but they have some conflict of the schedule, so they have there today. Okay. Again, thank you to coming and hope to enjoy for today. If you have something that you would like to suggest, please tell me. Welcome. Thank you.
Okay, thank you, Dr. Asis. And then we will begin for the first session. May I introduce the session chair? The first session chair is Associate Professor Dr. Bunseum and Associate Professor Dr. Surachet. Okay, I will let him introduce other speakers.
Ladies and gentlemen, welcome to the first session of the seminars. Well, in this session, we will hear about the, how will computer change our research in different perspectives. So the first speaker, may I welcome Professor Dr. Chi Seng Chan from Malayan University. Please welcome.
Thank you very much. So thank you, organizer, for inviting me for giving this presentation. I'm sorry that I have other commitments, so I will not able to travel to Thailand this round. But anyway, I hope to see you all. Like days in the future. So what I'll try to present today, according to the team, how computing will change the research. But for this, I'll be more focused on eventually on a particular topic that I've been doing with my universities, as well as some of the civic council back in Malaysia. All right. So this is, if you can see my slides, hold on. I think probably I'll just give me a second. I think the presentation. Yeah. Okay. So this is it. Okay. So particular focus on long-term video surveillance. So if you look at the aim of this area of work, okay, is to video surveillance. We can take on different perspectives. Okay, we look at the habitual behaviors of people or permanent changes to object. All right. So in this kind of context, our work or our research, we would like to investigate how these operation patterns can be extracted over a long period of time to gain high level of understanding for various factors at play. So of course, you might wonder, what to do with computing. So if you look at the collaboration, eventually is between the universities and Intel corporations. So of course, this whole thing, we split the scope. So between our university as well, we only focus on the personal ID. We do have another universities that come to join us in between. They focus on the action recognition. And then very importantly, if we look at on here, eventually Intel is one of our key players where they provide the data center architecture. So I'll explain more on that. Why do we need Intel in this project? So long-term surveillance, so everyone knows, at the moment, CCTV are quite common in almost everywhere. So this is exactly a typical scenario in the control rooms. So you have more than one cameras that you need to see cut across a lot of monitors. So there's no doubt about that humans can do this thing well. So then we are looking at humans versus computer. Okay, so as I said, I mean, there's no doubt about humans have that kind of capability of do this kind of job. But however, this happens. All right, I mean, human will fatigue. I mean, research have shown that humans are only able to have a very short span of concentration time. So with this kind of continuous or repetitive monitoring activities, eventually, I mean, humans will have this kind of out of focus of tired. So that's why we look into how eventually to utilize, I mean, the computing resources, okay, to help us to do this kind of a video surveillance in much more better way. So, for example, okay, we split this kind of work into routine premises, or which is looking at person ID, trajectory profiling, to a large more scale, looking at within a city, which is for person searching and trajectory predictions. So, for example, this is what we put on the campus demo. So now, eventually, you can able to, using computing power with some algorithms, you're able to look into, focus on the object that's moved. I mean, across the video, we can see that the left-hand side is the original video that you always see in a typical setting. But on the right, eventually we use the computer resources, an algorithm. We filter out the background, and then we only focus the things that move. So this is one of the first steps that we have using computing power to help the guards or the humans, I mean, to perform their daily job in a much more effective way. So after that, I mean, when computing power getting better and better, not just that we can do single cameras, but we can do multiple cameras. In this kind of case, is called tracking. Previously, we don't do any tracking at all. As long as there's an object move, okay, then it will be shown on the screen. But now, with better computing power, I mean, as years goes by, you're able to do much more complex scenarios. So in this case, this is a multiple camera scenario in a stations. So what we are interested is to track this suspect, which is wearing a yellow shirt. So on here, you can see that eventually, I mean, the camera somehow automated adjusts accordingly, I mean, to the nearest to this subject, and then continue to track across the screen. So as I say, I mean, humans is able to do the same task, but it's just that, I mean, given that the person moving from one camera to the other camera, so it's a bit hard for human eventually to search in such a quick way where this subject has been moved on. But with computing power, I mean, eventually we can do this thing in much more easier way. So then, by single persons, okay, we extend it to multiple person. So again, this ones utilize even stronger computational power. So in here, the whole interest is to look into that to perform what we call the human counting. Eventually, how many people is in the station. So this is so dynamic. So eventually, I mean, this we can see that it changed with computing power. It changed the whole perspective of what we can do, and it's always beyond our imaginations. All right. So once we move on that, eventually we move on to look into tracking of face. Okay. So we started off with person trajectory tracking. Now we move to face, and you can see that, I mean, the facial technology that we have been using now has been quite consistent for the past few years compared to previously. Is because, I mean, everyone's know because of the deep learning algorithm. And as we all know by, I mean, deep learning algorithm not just hungry for data, eventually is hungry for GPU resources as well. So you can see that, I mean, we can do the face recognition tracking very well with this kind of resources, even though, I mean, in a video clips like this, that the face can be very small. Changes of clip in clip of seconds, the tracking of the face, I mean, still, I mean, the delay, I mean, is only in milliseconds. So you can look at that, I mean, how strong the CPU power, okay, back in before year of 2000 to what the combination of CPU and GPU at the current computing resources that we have been using or utilize, I mean, to train or a better algorithm, I mean, to do a lot of different computing tasks. So what I just show you on here is just a very simple example in the surveillance domains only. So then, I mean, given that we're able to track the face and our previous experience in tracking trajectories, what the next project that we have that utilizing both the CPU power, the GPU power, and the cloud services in here is that eventually we are not just tracking, I mean, whether the person goes, eventually we also would like to understand which trajectory or which path of road eventually this group of people are using when they travel on this street. And the reason is that we was approached by a commercial or marketing companies. They would like to know eventually on this street how people usually will walk from left to right or right to left, so that they can place the advertisement boards in a correct place that will attract the maximum attentions. So this is why, I mean, we need to utilize the hit detection as well as the trajectory tracking on here. And all these things, I mean, not just that it needs to track these two multimodal, but it also needs to be done a real time. So that's why, I mean, computational power, I mean, really help us a lot in this kind of mechanism. Same goes to this is a shopping mall of tracking. I mean, that we do back in 2017. So if you look at, I mean, the very earlier work that I presented, just do a single camera or tracking that is back in the 2010 or 2012 to 2017, where we have the CPU and GPU power combination. You can see that the tracking can have more mechanisms in the sense that not just that we're able to track the face, we're also able to track their movements. We're also able to detect or recognize their attire. So you can see that the transition of this, not just that we have a better algorithm, but eventually is also we have better computing resources that are able to drive this algorithm to be more complex to do what we are able to do now.
Excuse me,
so,
sir.
Same thing. I mean, we are due, this is what a project to be done again on the visual surveillance. So you can see that, I mean, we track every person that coming down from the escalator. And then this is what is on persons searching. Okay, we try to look for particular persons in a typical scenario. So this is real-time scenario. Again, is a combination of cloud computing because we need to have the access of the data in any time, anywhere. So that's why we need to utilize the cloud services, and then the GPU services as well in this kind of mechanism.
Okay.
So again, I mean, you can see that back in 2005, when we start to do another we do traffic monitoring system, we can see that the limitation of what we can do. You can see that, I mean, the algorithm is not that perfect because the limitation of the GPU that we're able to use. So it limits us to design a good algorithm. So as you can see, when the car passes by to a region of interest, somehow it has some confusions. Okay, it has some confusions. But as I mentioned, I mean, with the bloom of deep learning and the GPU power back in 2017 and up to now, eventually you can see that, I mean, we have been able to track the vehicles, more effectively. I would say not perfect, but more effectively. As from here you can see that we will not really suffer from the illuminations problem. We're still able to track every car, classify them into sedans, lorry, SUV, and so on and so forth. And then not just that, you can look at a single way. Eventually, you can also look at multiple way. You can separate the type of vehicles to the vehicles or motorcycles. So as a whole, the
Excuse me, sir.
transitions of
Could you hear me?
computing,
Excuse me, sir.
facilities, okay,
Professor.
has really helped us a lot. When we try to do a artificial intelligence algorithm in this moment. So what I've shared with you just now is some of the samples that what we have done back in 2000 with CPU resource only to what we have done lately with a combination of CPU and GPU plus the cloud computing. So this is a typical computing facilities that we have now. In almost every institutions or in companies. Okay, not just that. We do have a storage cluster, but if you look at the main difference eventually is on the compute cluster. This is on the most right on the screen. We have CPU nodes, okay, and GPU nodes, okay, because way before the year of 2000, eventually, GPU are not really popular. As a hardware or tools in research. It's because of the emerge of deep learning. Eventually, you can see that a lot of the GPU has been using in research community rather than the gaming industry. All right. So this is a typical one. And at the moment, as I'm going to share with you, this is somehow the facilities that I do have back in my university. Of course, it's not extensive, but it has enabled me, to look into how to strategize on what algorithm eventually, are able to utilize. So that's why there is a very tight relationship between, I would say, the computing facilities and the algorithm that you would like to design. So this is always my guideline for myself and also for my students. When we embark on a new project or new research directions, we always look into this before we really go into the design of our algorithm. Because, for example, on the GPU, we do have K10, K40, Titan, and V100. V100 is our latest GPU that we just bought it last year. So I need to strategize that what I can do, what I can't do. On this. Okay. So I think that's all my sharing for this morning. So thank you very much for your attention.
Thank you very much, Professor Dr. Chi Seng Chan, for a very interesting topic. And I think it's not just that, because we can contact you later for the further information. It's very interesting. Thank you very much. Let me introduce you the next speaker. The next speaker is Assistant Professor Dr. Aziz Nantamon Pong from Prince Songkhla University. Please. Thank you.
Okay. Good morning, everyone. Again, I'd like to talk about actually some of the research of our team. The AI task is our research teams. It came from the Endowment Intelligent Tourism and Service Information Center. Okay. See me? And the mobile.หน้าเดียววะเหรอเอ้ยมีหน้าเดียวอ่ะ Okay, it seems that this my slide is have a problem because it has only one page. So I can switch to the next one and I can answer you. Okay.
Sorry for the incident. Well, for the next speaker, I would like to invite Assistant Professor Dr. Varodom Veerapan from Prince of Songkla University as well. Welcome.
Okay, thank you. Good morning. Today I'm gonna present about the blockchain because I'm doing my research about the blockchain and its application, what the blockchain application can be implemented nowadays. Before we're going to describe the blockchain, I would like to introduce my research team, as I am the team leader of the research team. We have several lecturers from COC and other lecturers from technology environment and master student. And moreover, we have another professor from Vishwakarma University from India. This is our research team, and we have some collaboration. So I will gonna give the concept about the blockchain, and then followed by our study project that use blockchain to implement it. So I give a short describe to motivate and to introduction about the trust and problem in the computing world. We can separate to type like centralized or distributed. In the centralized, everyone go to the center, so they have pro and cons. If we say to cons of the centralized, it's easy to have attacks, and there are some fault tolerance, and they can have like collision resistance, which contrast to distributed. However, the pro in the distributed may be con on the centralized, and the pro in centralized may be cons in the distributed. And the blockchain is one of the distributed system or decentralized system that try to remove an intermediate node. And the use case that we frequently see is about financial. For example, like nowadays, if we would like to do some money transfer, we have to trust the bank. Like the bank is the central entity. Oh, sorry, I forgot to share my screen. Because we have a live session, so we need to share screen too. Okay, so we continue. I just first give introduction about the blockchain. And so what the blockchain is, actually blockchain is a going list of the records called blocks, which are linked using cryptographic. And blockchain has known for a long time ago, but the other use case like Bitcoin created by Satoshi Nakamoto is just proposed on 2009. The concept of blockchain, we connect the block using a cryptographic hash. I won't go much detail. I think whether here all know the basic, so I just skip it. But I can say the word of summarize what the blockchain is for other audience. In my view, I think blockchain is like a database with some special features. What are special features like transparency, immutable? We cannot change, and so that's why we can trust the transaction stored in the blockchain database. And then I will go to our study project. We implement several study projects. This is the first project that we are already implemented. We call the PSU coin. We issue the token in the standard of ERC20. And what is the use case? We use this token to represent some the student activity credit. Like before the student graduated, student need to do some activity. And the problem is sometimes when we create the activity, the student not tempting or not motivated to join because the incentive, and sometimes if they already done if they have enough student credit, they want to join the activity anymore. So we create the token to motivate or to incentivize. And when students got the token like a PSU coin, we can link this token to other activity, like we can use this token to vote, as we think that the students who contribute to the university, they will know more how the way that university should do or should implement the mechanism or the projects. And although they can use token for other activities. The next one, we use like solar energy credits. These projects, we also tokenize the token like ERC20 to do some fundraising. And this is the concept idea to use blockchain as a database to store a single database of the patient. Of course, the privacy is another thing, but we can have some problem to solve this problem. And this is another quite large project that the police also asked us about the blockchain, because they got a report from there are some victims the victim has been scammed by the thief, and the police had no idea who is the thief. The only information they have is just the thief wallet address. So we try to do some transaction analysis linked to the exchange, because the exchange know the identity of the person who do the transaction. And this is a arbitrage system that when we would like to do some thing to buy the token with the high price and sell back to the low price, and we got the profit from the different price buy thing. If we do it manually, it's quite different because the price is changing very fast. So we write some searching algorithm to search the price at the several exchange, or centralized exchange and decentralized exchange, and find the opportunity and execute the transaction in a second using a smart contract. And this is a blockchain-based review. That the property of the blockchain that the transaction cannot be modified. So if we store the review from the hotel, it means that it cannot be cheated, and or it's not easily to cheat. And we implement the blockchain-based review to the hotels. And also we also implement the voting system that we can use the blockchain. The person who vote, they need to have a token to vote. And the voting result is not easy to cheat because the immutable property of the blockchain. And also the NFT game, when they play the NFT game, they got some NFT token that motivate them to push to put effort to learn, because they not only to get the knowledge, but they also got the token, and we can link the token for some benefits. And pity that we have less of time, but so I cannot go in much detail for each project. But if you're interested in any project or other project that I haven't seen, but it's relating to the blockchain, you can talk with me later or in the discussion panel. Okay, thank you very much.
Thank you very much, Professor Varodom, for the interesting idea. What I like the most is the interesting idea that that you use PSU coin to motivate the students.
Yes.
Then they can use they can get the rewards more
Right.
than just only the study performance.
Right.
That's great. That's great.
Thank
You so much. So for the next speaker, we will come back to Assistant Professor Dr. Aziz Nanta Amonpong from Prince of Songkla University. Okay. As we have seen from previously, it would be about the tourism related topics that we the team used computing for tourism applications. Please bear with the technical problem for a minute.
Sorry, that's a problem. Okay. As I work in the Phuket, so the Phuket is a very much tourist destination. So if you look at in the statistic of the income of the Thailand, the most income is come from tourism, and most of them come from the foreign tourists. Okay. In right now that the right now in tourism that the social media plays an important key role for attract the tourists. Like the many tourists before making the decision, they will look at the some website or from the social media, like the post photos something, and then we will make a decision to come from to Phuket or any place on any place in Thailand. But I would like to tell you one story that in the time of the COVID-19, we Phuket have a project like the Phuket Sandbox. They try to have the program to allow the foreign tourists to come to Phuket, but have some procedure. And in that time, we have some, some bad news on the social, like one of the tourists post that they are so expensive taxi from airport to the city, like 900 baht. And only this one post is have negative effect all of the Phuket tourism industry. At this story, the governor of Phuket called many organization and agency to have a meeting about this. Only one post about the taxi is very expensive, right? So this is an idea is make us to work on how we can know that what happened in the social media, right? We would like to know what the community in the social media talk about the Phuket. So we use some technique on the machine learning and text mining, like the topic modeling to group the text, the post from the social medias. We in this research we use the LDA, the latent literature allocation, is like techniques to group the similar topic together. The theory of the LDA, some of that, and we are not the first group to use the LDA with the tourism based data. There are many other POS work to use that, but it's a different objective to use that. To the methodology to this research, we use only the simple things like on the text mining process, like we are collect the data, and we have used pre-process and process the data. Okay, we also use to classify the topics in LDA. We use a coherence score to work on that. I would not tell you for the more detail in the techniques. And after we work on that, we classify the topic, like 8 topics on that. But these topics are based on the data from October 12, 2004 to 10 March 2021. There are like 60,000 comments. Actually, but now this project is still going on. So right now we have more like million comments from like trip advisors and from other Facebook, Twitter. Now we find the new problems, how to handle with the one or more than millions data. So we just bought no, just we bought the new server with the high CPU and GPU, but now it's 3 months. The factory did not send us. They say that they have a shortage of CPU and GPU manufacturer, so we are still waiting on that. Based on the LDA, we can know which topic is the most topic that the people talk in the social community and the social online. Like for the trip plan, it was most mentioned in the social media, right? We did not only the extract process the data, we also we are now developing the platform development to show that in the dashboard or in terms of some other data visualization. And this is some capture from the platform we made it. In the platform, we can automate process the data and show the result into the website. But now it's not completed, so I cannot show you for now. But in the dashboard, it can show which keyword that have many percentage of that. As some examples. Okay, sorry about the the delay of my presentation. So I would like to know that I would like to tell that for my research and my research team, we focus on the data on the tourism and many aspects, like for business, for the government agency, and for the tourist. We are still going on this project and similar to project. Okay, thank you.
Thank you very much, Professor Dr. Aziz, for very interesting and applied application of your research to the tourism. The next speaker, let me invite Professor Dr. Andrew Bardsley, please. Thank you.
I can get up and stand. Okay, well, we'll see how it works out. If anybody wants me to get up and stand around, that's fine. So my name is Andrew Bardsley. I'm afraid I don't have any research to present today because it's been some time since I've actually done any. I did my PhD at Manchester University in 2000 in the subject of asynchronous logic synthesis, and I kind of describe myself as a tool developer. I build EDA tools and build systems for putting together computer systems. So I have to say, I'm kind of required by my employer to say at this point that I'm not here on an official basis. So anything I say later on that might seem to be a tidbit about what ARM is doing, please don't repeat, because I probably wasn't allowed to say it. So I believe I can give a better industrial outlook than I can give any sort of insight into current research. And ARM is very interested in research output from universities. But we do have an interesting angle on this, that we are a company that principally builds processing units. So we're always interested in what effect applications have on processing units and what we need to implement to make that possible for people. So we're interested in new instructions for CPUs. We're interested in new coprocessors. We're interested in completely different new and novel processing units that may be needed. We're very interested at this point in software optimization, and in particular, making things work in the cloud and improving the performance of software that might have been working on processors from other manufacturers. And we're also interested in AI, machine learning, neural networks, everything that is the use of lots of multiplication, and also in all platforms. So on all existing processing units, in platforms that already exist, in platforms that don't exist, and also, interestingly, in very small ones. So we're interested in microcontrollers with the ability to do neural network processing, for instance. Let me just refer to my notes. So ARM is sort of externally a consumer of research. The biggest thing we don't have is a large source of applications. So we're a company that builds things. We don't explore how they work as much as we'd like to, because obviously the economics of that are a bit of a restraint. So what we'd like to see from research is people bring to us novel novel processing requirements that we can't otherwise make ourselves. So it's probably useful for me to say what I actually do within ARM. I, as a toolsmith, actually build simulation systems for doing full system simulation. So I'm responsible for maintaining a system that brings together models from within other parts of ARM and within groups that develop pieces of IP that they build for their own purposes, and they do experimentation on in isolation. And we do system level experiments, so experiments to challenge the memory system or to challenge an integration of two pieces of IP in places they weren't designed to necessarily fit. And as part of that, we know exactly how the hardware is going to work. We know how to put it together. We sometimes manage to get the IP teams to tell us how to put it together properly, but we're usually starved for applications. We get to the point where people want experiments to be done. So someone wants an experiment to see the effect on a cache system of running multiple processing units of different types, and we don't have software to run on that. So potted applications and the reproducibility of research results and things coming from commercial sources is very important to us. I probably should also plug that what we want from students, as I believe the emphasis of the conference is also on what how students should be taught and what comes out of that. My group is looking for quite traditional requirements. We want students that know about system design. We want students that know about things like memory coherency and the effect on caching in systems and can think through the logic of that. But that deep knowledge you can get from a university, and that one step back and that analytical approach is also needed too. So unfortunately, there's a little bit of a balance involved in that. So I'm going to say a little bit about so just to sum up a little bit about the interested research areas for ARM. Image processing, AI, ML, as I say, interested in everything that's required in new places to put multipliers. In cloud computing, I think we're mostly interested in applications. We're interested in performance improvement, and we're making progress in getting hardware out there to be available for people to work on ARM processors. And in things like blockchain and crypto, I think we don't really know, but I probably shouldn't have said that. I suspect in the future, someone might come up with an instruction for a CPU that makes that more efficient, but I'm not really sure what direction that's going. So, that's me. That's all. That's all I have, I'm afraid. Yeah.
Okay, thank you very much for Dr. Andrew for the valuable industrial insights and outlook for research and also the student requirement. Thank you so much. So the next speaker, we have you have seen him already, Professor Dr. Kosin Chamnongthai from King Mongkut University of Technology, Thonburi.
อันนี้ไม่มีพูดได้เลยต้องย้ายสายนะครับต้องย้ายพวกนี้หมดเลย
Okay, good morning. I start my presentation now. Let's see this slide. You can see the orbit of the planets. And in, you know, Galileo, you know, Kepler, and Galileo come first, maybe 100 years before Kepler. And the right-hand side, you can see the orbit of the planet. It is circle. But after that, Kepler proposed ellipse as the orbit. And I mean, Kepler collect how to calculate the orbit. Okay. And what happened? I went to Austria once, maybe 10 years ago, to see my friend in Linz. You can see Linz in the map. It is in the northeastern Austria. You can see Vienna in the right-hand side of Austria. We go by train to Linz, and in Linz, surprisingly, my friend made this one, solar clock, and he followed Kepler, and he proved that Kepler is correct. It's ellipse, not the circle. So what we learn from this case, you can see ellipse in the pamphlet, in the brochure, and the solar clock. You can see here to the orbit and make you can see the time from this clock. And what we learn from this case study is first thing, what we invent or what are our research results now is correct, but in the future maybe become incorrect. Okay, so what you do now is okay, but in the future someone will be better. And another thing is, this is related to our theme. We in innovation, in technology, in engineering, we try to approximate. This is my keyword. Approximate. Based on mathematics, we utilize or we apply mathematics to implement something. So the existing mathematics is circle, ellipse, rectangle, only those things that we can use. So we cannot represent any shapes now. And this is out of my talk. You can see the picture on the wall of the building. This one was hidden long time ago, because it was a war between, I think, Roman Catholics and Protestant, okay? And it's open for public now. I mean, someone found that one, so I just out of the title, and you can see a mosaic, right, to cross the sea, escape from the enemy and make the sea. So, very beautiful. Okay, let's come back to my title. This is near the solar clock, okay, in Linz. And I introduce you 3 or 4 cases up to the time. This one is the method to find a shape of skin cancer. We try to segment skin cancer, because when the medical doctor perform surgery, they have to draw the boundary of the skin cancer. If it is too much, maybe the skin remains. Okay, too much may be painful for the patient, but it's too less. What happened? The cancer still remain. Okay, so we try to correctly segment. And the left hand side, we learn that snake is the best thing for segmentation in this case. And the problem of snake is parameter and initialization. So the left-hand side, the most left upper picture, you can see the most appropriate parameter and initialization. And figure B, it is the red line is result of segmentation. The blue line is initialization. So if initialization is suitable with suitable parameter, very good. But we try to implement automatic system. So in figure C, you can see we use circle or what we call geometric shape because we cannot use any shape in mathematics. Okay, we cannot use any mathematic model. So what I would like to tell you is actually we succeed to use geometric shape to initialize segmentation using snake. And what we learned from this one is we can use only existing mathematics, okay, and what we call approximate, okay, to implement the system. And this one is the case study of moisture measurement. So in the lice contained in the any shape and any size container. So we use microwave and attenuation. You can see in the left-hand side the graph. The vertical axis is moisture, and the horizontal axis is attenuation. And the shape of what we measure to obtain moisture look like tangent. Okay, so you are a computer man. You know that if you want to the horizontal axis show input and you get the output, what do? You use lookup table, right? It's really huge size of lookup table. But if you use tangent in the equation, just one mathematic model. So we respect mathematics, okay? But it is limit. So we have to approximate. We cannot represent correctly. And also this one is another case study to use mathematics to implement this automatic system. We try to categorize vehicle types at nighttime and use thermal image. You can see the type of vehicle and thermal image. This is 3 dimension and convert into 2 dimension. What you can see as the shape, Gaussian, right? So we use Gaussian to represent, use a mathematic model of Gaussian to represent. Otherwise, you use a big size of lookup table. And also this one is another case study of gas detection. In the near future, maybe you don't use finger to touch, to talk with the machine, but someone, the patient who cannot use the finger, they use gaze to talk with the machine. So this one developed for gaze detection for human-machine interaction. And you can see the gaze direction to the target. Okay, and we use the eye tracker as sensor to detect. Okay, and okay, last one. What I would like to conclude is the bottom is mathematics knowledge. To implement something or innovation, you need imagination. Okay, so researchers use imagination based on mathematics knowledge. But the thing that in the near future we have to adapt is competency of tool usage. What I would like to talk to you is imagination and mathematics model. We have to learn, we have to know it's the same. But in the near future, the top one is the problem. Okay. Thank you very much. Sorry for the day.
Thank you very much, Professor Dr. Gosin, and for the very remarkable conclusion on your work and your thought. Okay, let me introduce you the next speaker, Assistant Professor Dr. Dharani Homdi from Khon Kaen University. Please, thank you.
Good morning. And it's nice to be back here in Phuket and at COC as well. Actually, my talk is not really related to anything much because, how can I say? This is the topic that Professor Gosin gave to everybody. So in trying to stick with the subject here. But what I'm going to say is, firstly, as you heard from Dr. Andrew already, he's my classmate from Manchester time. And what we've done there is more like about the machine, the chip design. So it's quite far away from what I'm doing here at the moment. This is the research I'm doing collaborated with medical school or the Faculty of Medicine in Khon Kaen University. Actually, they started before my time, like 15 years ago, I think. The thing that they built is like a laparoscopic robotic surgery system. And in the past, it's just about the machine. So it has been designed and implemented by mechanical engineers and architects and a little bit of electrical engineers. But nowadays, computing takes part quite, dramatically and a lot in terms of, in the past, it's just only the machine, but now they add on some smart and intelligent system into it. So right now, there are like 3 parts. The machine itself, which is, this is just only like a cartoon thing that we drew because the real machine is quite, I don't know, I think it's ugly. That's the prototype and you don't want to use it, let's say. It's mainly for hysterectomy, so it's for women. Mainly that we're doing here. This is a single port laparoscopic what they call equipment that use in the past for laparoscopic surgery. They used like 3 holes. You need to like insert the equipment, laparoscopes, and some sort of like other relevant equipments into it. But this machine, you use just only 1 hole. And you just stick 3 or 4 things into it. And it has been designed by a assistant professor from Rajmangala, Isan in Khon Kaen campus. And what they've done, this is the design. I'm not going to go into it. But then in the past, as I said, is more mechanic stuff. But now they use like a PLC, and what we've done is feedback the pictures from it, and then just use like AI by deep learning to detect things like instruments, organs, and in the near future, we hope that we could do surgery without doctor. It sounds scary, but that's our dream. The second part is about visualization. So this is what I meant, the detection. And we need to detect like uterus and what else? Tubes, like fallopian tubes. That's what we aim for, to have what they call tubal, what it's called, let me see, tubal sterilization. that has been done without doctors, so it's going to be automatically for somehow. So basically, we just need to detect where the tube is and maneuver the machine, and then just cut it. It sounds easy, but at the moment, we have done just in the soft issue cadaver because of the ethic things. It's quite difficult to get. So either we do it in the pig or cadaver. Oh, it should move, but okay. Anyway, what we've done is just in the before that we use like a public YouTube clips to teach the machine, and then later on we have a lot more clips from the real operations. And this day, what we've done is we use, as I said, cadaver. It's going to be soft issue, so people are dead for 2 to 3 days only. Otherwise, everything's going to be completely ruined, and you can't you can't detect anything anyway. So the third part is about instrument that we decide. It's a manipulator that gonna do with a uterus. Basically, when they do this sort of operation, they stick this sort of machine by the vagina and just control the uterus the way we want in order to move around and find the tube, or even do the hysterectomy. So it's like completely remove the uterus. This machine has been designed by using the existing instrument that has to be tunable. It has to be recycled as well, recyclable. So everything can be sterile apart from the machine outside that you can see here. It's quite simple. The 2 motors and then just 2 DOFs. And this is the simulated 3D uterus that we use to make sure that the angles and the strength of the machine won't destroy the organ of the patients, let's say. And what else? This is what I just trying to make it a little bit blur and small, so you don't need to be too scared. The first time I entered that sort of room, 2 of my students fainted because we don't really get used to and just leave the atmosphere inside. But this is just the cadaver. The first few months, we just need to observe, get the requirements, and then later on we built the machines and just go to test it. In the near future, as I said, we plan to have it tested in the real patients. What I'm going to say now is in August 24th to 26th, Khon Kaen University will organize the ACCAS conference, which is ASEAN Conference on Computer-Aided Surgery and Medicine. And the thing is, we plan to have the live operation by using this machine to show, the world that what we can do, and everybody's welcome. And I hope that you could submit the paper by, I think, the end of June, but we can extend it for all of you to come to Khon Kaen. That should be it for the now. Thank you very much.
Thank you very much, Professor Dr. Dharani. It's a very exciting application for computing, and it's very important. Thank you so much. Okay. Well, for the last but not least speaker for this session, I would like to welcome you all for Professor Dr. Prapat Chongsathitwattana from Chulalongkorn University. Please welcome Dr. Professor Prapat.
Okay, right. Thank you, the organizer, to invite me. Although Kosin and myself is a friend for long time. All right. I present a bit of my work so that we can get to know each other a little bit more. So today, this morning, I like to show you a little bit of what now we are in the kind of post-classical, right, computing. So there's a lot of interest in experimenting with the future computing machine. So my work here is to program. Supposedly that machine is available now in the simulation. In the near future, then how can we use this futuristic machine to solve some of engineering problem? So I start with the doing some kind of optimization. Okay, and you can imagine this as a kind of learn how to program quantum computer, that sort of thing. Okay. Oh, right. So I skip the introduction and right. I want to use a quantum computer to do optimization. So I start with the method that I'm most familiar with. It's a evolutionary algorithm, or as a well-known name is a genetic algorithm. And we have some special version of that in which we can represent the searching space, the solution in the search in our searching space as a set of data, not as each individual data, but as a probability density function. Okay. So we call that a compact genetic algorithm. I think it invented by Professor Goldberg around 1990. And I want to convert that algorithm to run on quantum computer and study the behavior, if it's faster or slower, or what kind of behavior it is when it runs on quantum computer. Okay. And to do that, because the quantum computer is totally different from classical machine. So the way we do a searching, we use a classic Grover algorithm. So that had to be incorporated into the modified genetic algorithm that run on quantum computer. Okay, I will skip the basic, right? Okay, so it is the actual algorithm on classic machine. And briefly, we have a probability density function. So we sample the solution from that space, and then we maybe randomly pick two solutions, and then because this is optimization problem, then we evaluate according to objective function, and then we say, okay, this one is better. Then we modify that probability density function to be more like the winner. Okay, this is a classic. Okay, so this is how the compact genetic algorithm works. All right. So this is well studied since 1990, and we have a lot of knowledge about theoretical limit and practical use and so on. So that is the basis of a version that we want to run on quantum computer. For the Grover search, actually the main idea is when we search in what they call quantum memory. This is a function that Grover uses. If we can ask this kind of question for the value of x, that fx is equal to k. Okay, it is kind of one operation over the whole space. So this is why quantum search can be much faster than classic. Okay. I think Grover is one of the most important discovery, okay, that we can make use of quantum memory to perform computation. I will skip the theoretical detail. Actually, the work I present here already published, so you can search my webpage with the name of similar name for the actual paper that you can read in detail. All right, so this is our version. I will explain the idea first, and then show you the program on quantum computer just a few slides later. We use the quantum circuit to generate the individual, okay, and then map that individual into a kind of optimizer based on a grid of, we call Ising spin, a bit technical. And then this must be combined with classic computer to evaluate the objective function and then to reconfigure the quantum program and run another round. This is the current state of technology on quantum computer. Nothing I can do about that. Okay, it is not a pure quantum computer that we can execute it. It has to be connected as a kind of hybrid to the classic machine. Okay. Oh, so this is the first stage. The lower left-hand side is the problem we solve using this optimizer is the classic Turing salesperson. Okay, and the amount or the size problem is very small because the simulating quantum computer require a lot of resources, and we use the one IBM made publicly available. So the maximum size that we can solve is I show you 3 cities, which is tiny, and 4 cities, and we are writing the manuscript for publishing for 5 cities. Okay. So this version show you I think 3 cities, and it requires 4 quantum bits. So the first circuit on the left hand side is to generate the possible solution for this problem. Okay, and we have to, I forgot the one slide. We have to check the validity of the circuit of the solution. Okay, and then the first circuit will be what they call search for including global search into this circuit. Search for the best solution. Okay, that is one round, and this is how we map the graph problem into Ising spin. Okay, this is a bit technical, but it in terms of a matrix of 0 and 1. Okay, and then we can flatten this into a qubit. So for these 3 city TSP, it requires 9 qubits. Okay. This have to be think very cleverly before we can solve the problem with quantum computer. So this is one of the ingenuity we have to come up with. This is not my own idea. Okay, I read the paper from other people. I just compose everything together. Okay, so this is how we check validity of the circuit of the solution. And okay, the interesting bit is this here on the graph on the right hand side. We compare the classic with the quantum based on the number of solution we have to evaluate. And you can see that the bottom line, the best one, okay, the vertical is the number of function, so the cost, okay, and the horizontal line is the space, okay, the more resolution space require more time, okay. So classic is still the best, and the bottom line it require least cost. The rest is the different configuration we try to run the quantum circuit. This is not about the runtime, okay, because with the existing hardware or technology, we don't know, okay, and I did run this program in simulation, okay. So that did show me that at least the optimizer that I proposed behave very similar to running on the classic computer. It doesn't mean it runs faster or slower, because all the configuration can be evaluated in parallel, okay. And it did not, what they call it, we don't have the real machine. Actually, we do have the real machine, but the real machine is so slow. It make no point to compare it. So that's all. Yeah, and hope you can see that the quantum computer already arrived, and then we can make use of it. But the machine that we can try to use is too small right now. But it will be, as usual, the hardware, and you may agree, improve exponentially, right? Okay, thank you, everyone.
Thank you very much, Professor Dr. Prapat, for very advanced topic in terms of the quantum computing. And I think we have come to the end of this morning, I mean the first session in the morning, and we have around 15 minutes break. And we come back to this room again at 11 a.m. Okay, thank you very much.
Well, I'm going to have to learn from you. I cannot sing. Do you have your own YouTube, yeah. Okay, let me see this. Yeah. Does anyone watch your television? Yeah, exactly. So I think what we're going to do is we find and what we เอา ว่ายาวได้เกินขับได้นอนตั้งแต่นู่นแล้วอะไรนะครับ
we should start the next session now.
Okay, welcome back, everyone. We're gonna come into the second session of discussion today. The first speaker we would like to talk in in this session is Associate Professor Dr. Bunseum Keo Kamneut Pong from KMUTT. Right, welcome.
Hi. Well, my name is Bunseum Kamneut Pong. So this session would be about the a case study in human factor engineering research. So this is a little bit about me. So in the future, if you would like to talk about me, there's other things. My background is in computer engineering, mechatronics, and also the computer science. And if there's extra curriculum that I also interest is in coaching, meditations, and also the investment. So if you would like to talk about, well, a few years back, we have a lot of talk about the design thinking that we can use it for develop product that is suitable for the users, right? And the framework is very easy. So we need to empathize people, and then we define the problem to find the real problem, and then test it, right? But the problem is to understand the human needs and real problem is very difficult to achieve. So it needs a lot of skill in order to understand real people needs. So it's kind of complex, and then also the complicated things to do. So you need a lot of experience to do so. So in our research group, we just founded a few years back, and we're trying to use computing in order to collect the data from human factors, everything that we can experience from human, and we use it for do the product development. And this is example of the product that we built in our lab. So this is our team, and a part of me, that would be another 4 professors. And this is the concept of our team, that we would like to use research as one part of to announce things that we study about, and then trying to get information from the real user through the startup company, the robot friends, this ones. So we have the target group in autistic children and also the elderly. We would like to have the real users feedbacks from them in order to come back and then trying to understand more and build more research and then gain more students. And this is the cycle that we're trying to do. So in this talk, I would like to give you some example that we have done in the past 6 years. This is about this robot. We call it Blitz. So it's the robot for learning intervention to promote skills for children. So in our idea, one size doesn't fit all. So we would like to provide the personalized learning for children with special needs. So in this case, we are studying with autistic children. So you might have known that about 1 in 10 children this day will have disability. Well, either physical disability and also mental disability. So autism or ADHD or learning disorder is also mental disability is counted as one of them. And there are a lot of people in this world that have these kind of things. And it also needs a lot of money. And the problem seems to be, well, not better, not really resolved, because if you experience with this kind of children, it's very difficult to deal with. You need a lot of patience. You need a lot of well, care that you need to put into the actions. So not so many specialists that would like to come into this field. So the number of the specialists to support a growing number of the children with special needs is not quite comparable. And frequently negative emotion is become like a influence that obstruct their potential as well. And it's also come back to the specialists or the parents who has these kind of children as well. They also have mental problem as well. So if we do nothing, the society would be, not getting better. So we built this robot as a medium to play with children. So we think that through playing game with the robot, the children would be able to enjoy and learn things a little bit better. So we designed this one, and then we also do the experiment with the autistic children. So this is our system. The robots, it's hardware, right? So it's kind of have some kind of limitation on computing a little bit. So we do some kind of computing on the robots, and the thing that is harder to process would be on the cloud, and then it will report on the application to the specialists and also the parents. So this is the concept that we take it right now. So it's like parents at home with the children, and then they can together they can play games. And for example, like this one is the picture matching. So for small children, it's very useful. And the robot will give feedback that is motivate children to pay more. And we can also change the games. And the robot will collect all of the data from the children and trying to process and personalize for the children to get better, hopefully. And we can also analyze the data after the play, and also has the medium for the parents and also the specialists to exchange information on how to take care of the children at home. So this is our timeline, and we started about 2014 and developed the first prototype. And what I say is difficult because we have to, in that time, it's not so, the hardware is not so sophisticated. So we have to see and take a look by ourselves and trying to gather data. And the data is just only the little things that we can have. So we have tested in Ramajapati Hospital in the freestyle mode. And later on, we also try in the clinical testing at Rajayanagul Institute. So after that, we take a loop of the design thinking, and then we develop the second versions and also test it again And now it's the third version already. And we are looking forward to test it at the children homes, hopefully within these years. And we're also looking forward to, towards to the real user, and then also get the feedback from them through the startup company that we found. So what I think that computing will do in the futures is that it will give us way to perceive situations, both in human and also the environment better, so that we don't have to do it ourselves. And we also, the computing also will give us ways to understand people better so that we could design more suitable products for humans. And it would also allow us to optimize human system interactions. And for my research is that it will certainly help us to achieve personalized service that really fit us. And in this research is in learning. Okay, thank you very much for the talks.
Thank you, Professor Bunsel. Thank you for the gripping talk, and we hope to learn more in the afternoon. Next speaker would be Assistant Professor Dr. Natapon Unsi from Mapalong University. The floor is yours.
Okay. Good morning, everyone. Thank you for having me today for discussing about the computing in our research. The topic that we're gonna talk is the same as everyone, but I'm gonna tell the evidence from my research, right? It's outline. So for about me, my background is eco engineering. I graduated from Consortium University and Chulalongkorn University, and then I turned myself into mathematical sciences, and I got the degree from New Jersey Institute of Technology, USA. Right, and now I'm currently working as an assistant professor of computer engineering at School of IT at Mapalong University in Chiang Rai, Thailand. My research interest actually is focused on signal processing, as specifically for acoustics and biomedical, and in more specific area, I work on Bayesian filtering and modeling. If you know the common filter, that's a very conventional Bayesian filtering, and I'm working on that, and followed by the particle filter. And of course, we cannot live without machine learning nowadays, both classical and modern machine learning, right? And also the applications could be the marriage of the above. They merge together. We cannot live without one of them, right? Basically, when I work on my dissertation, when I was a PhD student in the US, I work on the ocean acoustic. My advisor got a grant from the ZEU from the US Navy, and the problem was that how can we localize, or how can we identify the geoacoustic under the ocean? That's a problem. So the experiment was set by putting the explosive stars into the ocean, and then and then we got the data, and the top left, the data from the ocean, from the ocean that we got from the sensor, and this one is a time series. So the question is, how can we get this information from this one, and then the information of this can be used into identify or track the moving stars underwater. That's a problem that we get from the Navy. So it turns out that only simple data like this, how can we get those things, this very huge one from the ocean? So the computing comes into play. We need to analyze it in the frequency domain. So the top right, we get the spectrogram of the signal. The spectrogram of the data is just a Fourier transform. Let me put my mask off. The frequency domain of the data, and we trying to track that. You can see that the colorful out there, that's going to be the information that we would like to get it accurately in order to find the frequency of the signal. And the top, the bottom right, you can see that the blue is a noisy data from the ocean, but we would like to estimate it because we cannot know how the noise is going on, but we need to estimate that from the noisy data. And the red one is the estimated version of the frequency of the signal that we get. And what we do after that, we get the frequency. What we do next, we need to use this one for the inverse problem, and we can identify the 7 sound speed profile or even the water column depth, the sediment thickness of the ocean, and these are what we would like to get. And once we get this, we can what we can imagine about the ocean can come into reality. That's the thing, right? So in order to get these car PDFs, is huge computing. Bayesian filtering require complexity. They require computational expensive to get this one, because the PDF particle filtering, Bayesian filtering needs about MCMC method to get the approximated PDF. So it's very, very computationally expensive. And this is another one. After my PhD study, I continued working on that ocean acoustic as well. And you can take a look at the top panel. You see that the blue one is the data, and you take a look at them. You see it's like very noisy. You never imagine that it was data before. It's noisy data. But for the Bayesian filter, the powerful method like this can be used to estimate the signal back, the original signal back. So from the bottom one, you can see that the black one was the black one was said to be the original data, and when we have the noises, you get the blue one up there. But anyway, the Bayesian filter can estimate the original signal back very, very efficiently, and you can see that the green one is what I got from my proposed method. That's the thing. I published this one in the Journal of Applied Acoustics. Right? And also this one, and you can see the PDF for the noisy data in the frequency domain, and you can see that you cannot even see that how you can see some trend of that. The yellow line here is like the frequency content that we would like to estimate, and we use the particle filter or Bayesian filtering to estimate that, and we can get the black lines here. It's a modes or the frequency pattern of the acoustic signal, and we get that, and here used further to identify the geoacoustic in the ocean. That's later on, right? And this is another for 5 dB signal. 5 dB signal is very, very, very weak signal as well, and we can get very nice track of the frequency. So these are what I have been done and been doing up to now, because it's just like a very I'm very in love with it. It's very, 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 very interesting and very fun for me to do it. And not only that, after getting to the Mass Falun University, I also work with the professor from another school, especially for the School of Industrial Agronomy. All right, so we work on the post-harvest biology and technology project. Especially in Chiang Mai, we have pineapple pula, which is very, very the GMP crops in Chiang Mai, and also we got the PMU grant from the government to work on the guava and the mango, the Nam Dok Mai mangoes. Right, and this is one of our outcome from the project, that we use the image processing to identify the damage on the guava for the transportation, during the transportation, and we can use some sophisticated image processing because the transportation contains two factors that can affect the damage of the guava. The first thing is the vibration, and the second one is the impact. All right, the two factors happen to the crops a lot, so that we try to introduce to innovate the new algorithms or the idea how can we detect this one. But that's from my side. But from the other side, from those professor from school of agro industry, they design a package that can be used to protect this happening, all right, from air transport or even the road transport, right? So and for those of you who work on email processing, you know that the competition is very expensive. All right. And I also work on I work with my PhD student who are working with me now. We are trying to make particle filter or Bayesian filters make faster. As I mentioned, that particle filter or Bayesian filter is require a lot of computational expensive, but how we can improve it? We make it faster, but the similar accuracy, we're happy with that. Or if we do need, we do not need it to be online, online estimation, we can get more accuracy, but it can take time. That's fine. So that's the trade-off between the two. So we are trying to make it better. We use the G algorithm, the genetic algorithm. As I said, machine learning cannot live. We cannot live without machine learning. So we use machine learning to improve the Bayesian filtering, which is a classical filter, the classical filter to get a better result. And you can see that after using the algorithm, G algorithm, we get a better PDF. All right. For the detail, you can come to talk to. We can discuss by later for during the break. Right. Okay, we get better accuracy of that. And we also work on, we can also, we try to find what is the drawbacks of the particle filter. The main drawback is the resampling process in the particle filtering. So we, together with my advisor, working on, we published the review article on the particle filtering, the resampling process, and this we classify in that. I invite you, if you are doing computational using particle filter or MCMC, this paper should be a very good start to learn how particle filter works. Right? So there's a lot. Computing comes into everyone. It's inevitable to live without it. So for me, computing is not really changes my research. So it's essential of the research, right? That's my last speech for today. Stay at home. Thank you very much.
Thank you. It won't be your last speech because you're going to be here in the afternoon as well. So next speaker would be Associate Professor Dr. Surachet Kanpracha from Naresuan University. Okay,ค่ะ
Make it screen time. Okay, good morning, everyone. The topic that I'm going to talk today is about semi-analytical analysis for communication system. My name is Surachet Kanprasha from Naresuan University in the northern part of Thailand. My major is communication systems. Majorly, I work in the field of fiber optics. Okay, so it's related to communication systems, and one thing that we need to do is that to compute the performance of the communication system that we design. One thing that is an obstacle of our part is that it requires us to do more in terms of simulation, because we have to generate so many bits in order to get the performance of the design that we have done. The first, I'm going to talk about the communication system model and then the performance evaluation. Of course, and the next one is semi-analytical analysis, and the last one is conclusion, which should not take more than 10 minutes for the time required. Okay, the first one is that it's normal that today we in the year of the communication, everyone has our own mobile phones, of course. And what we require to have is that to have our signal, or in terms of the data, communicated correctly from the source to the receiving end. In this term is that require that when we send out our data, normally it's in the digital format now. And we send, for example, we use the Twitter or maybe the Facebook or any source of applications that we use normally right now. There's one thing that we cannot escape is that the noise, and of course the attenuation from the sending from one place to another. It requires the longer distance. It means that the lower noise, the lower power that we can have, and the effect of the noise will become dominant. And at the receiving end, there will be some error, of course, and we like to have that as small as possible. In terms of the communication engineer, we design the system and we try to evaluate what we can achieve in terms of the performance. And this is what we are going to do. In the simulation, we need to simulate in terms of generate bits as small as possible. So how many bits that we have to send in order to evaluate the performance of our system in terms of the design? Right now we're in a field of 5G, and I think the data rate that we have like to have is at over 1 gigabit per second. It means that we transmit more than 1,000 bits a second, or in the Wi-Fi Wi-Fi standard. Right now we have 556, right? And it's about 2 gigabit per second. So it means that we in this area, in this era, we require so many data. And in terms of the simulation to evaluate the performance, we need to generate as many bits as possible. This is our obstacle in terms of the simulation guide. Okay. As I discussed, the communication system right now is in the digital era, and we have one performance metrics that we use. It's a bit error rate. In terms of it is related to the probability of sending signal from one place to another. We like to have the bit error rate as small as possible. There's some standard, for example, for the voice communication, we require it to be like a less than 10 to the minus 5 or less. And for the data communication, we require it to be like a 10 to the minus 9. From this figure, especially in the terms of optical fiber, we require it to be 10 to the minus 9. It means that to get one error, we have to generate like a 10,000 bits. 1,000 million or gigabit, 1 gigabits, in order to figure out whether there is an error or not. When doing the simulation, 1 gigabit is not enough, because in sometimes we can get one error, in sometimes you don't get one error. So it means that we require to do many more bits than what we require. So it's related to the time consumption in terms of the computing. Okay, at this moment, so I think semi-analytical analysis has come to be an important role. In this slide, we can see that at the receiving end, on the left-hand side of your point of view, you can see that on the left we have like what we call the eye diagram. Okay, we sum up the received signal at the receiving end, and you can see that it looked like in the middle, it looks like an eye, and what we call is the eye diagram. It tells us the quality of the received signal, and from this point of view, we can use the knowledge of the probability theory in terms of PDF. I think many speakers before me has been talking about the PDF, which is a probability density function. In this communication system, we make use of that quite extensively. From this point, we use the eye diagram to evaluate the performance and to get the bit error rate. And it's related to the Q parameter, which is shown in the left-hand side. which is the bit rate is equal to Q function of the difference between the average value from the bit 1 and bit 0 over the summation of the standard deviation from the bit 1 and bit 0. This is a one normal solution when you're doing the semi-analytical analysis. This is what we need in terms of the evaluate the bit rate in this regard is require less number of bits than what we normally do in terms of doing the full simulation. I think what we have known normally is a Monte Carlo simulation. Okay, using this particular analysis, we can use less number of bits, and it's of course leads to the small number of time required, and is an alternative way to determine the bit error rate. I just actually a doctor sitting next to me just helped me doing this figure. Okay, doing some example showing that we have the theoretical solution for the 16 QAM in terms of the communication system. The 16 QAM is one type of modulation that is used normally right now. Theoretically, you can see that when you increase the EBO, and now I may call is a signal to noise ratio. When you increase it, the received bit error rate is reduced. And the red line is showing the theoretical result. And the blue stars that you see is from the semi-analytical analysis. It seems that both agree to each other. And normally, if you want to get the blue stars like this, we require more than probably a gigabit in order to get the result to be accurate. In this, we use semi-analytical analysis or method. We use only probably 1,000 or 10,000 bits in order to generate the eye diagram at the received signal and determine the averages and the standard deviations of the bit 1 and bit 0. And as you can see that the similar result are obtained. And this is one of the examples that probably related to the topic that we are discussing today is about how computing related or change our research. In my point of view as a communication guy, I think computation is very important, and how to make use of the basic knowledge in terms of the probability of mathematics is very important as well. And it can reduce the consumption time that we require in order to get our result. And I think that's all that I have. And of course, I think the last person has sent out the message, the last speech, right? And my last message is that life is beautiful. Please enjoy. Thank you.
Thank you so much. And shall we move to the next presenter, Associate Professor Thikapan Charanpong. He's from Department of Biomedical Engineering, Srinakarinthara Virod University from Thailand. Okay. The floor is yours.
Good morning, everyone in this room and in the online. My name is Thikapan Charanpong from Srinakarinthara Virod University. My topic is I will talk about the application of image processing research in my lab. I raised two examples that I'm doing in this project. Actually, I have four main research right now, but I select two topics to present today. The first one is controlling image viewer in operating room. And the second one is a wireless capsule image analysis. For the first one is we design a system that's more convenient. First expectation we design this system that's more convenient for the doctor, but the final result is seem not much convenient enough. We design the system to interact with the computer with a touchless that is a touchless system by use hand movement direction. Our motivation is actually this project come from a doctor at the Signal Hospital. But after we study about statistics from the operating case of the world, there are the infection rates about 4%. That is very important for the patients. So touchless sterile equipment in the operating room should be sterilized. So including computer mice and keyboard in the operating room. During the doctor do the operation, they have to see the computer, see the X-ray image in the screen, and they use a mouse and control the image on the skin. And this is a cause of infection. The doctor needs a touchless device to reduce the infection rates, and easy to use and friendly for the user and robustness. We design the system by using user interface. This we capture the image by using a 3D camera and study the movement pattern like this. Oh, ไม่เป็นไร and this first version, the user will move their hand and control the image on the screen. But the basic function is just move left, move right, and zoom in, zoom out, and increase and decrease the contrast.ปิดเลยก็ได้ เดี๋ยวข้ามสไลด์ไปเลยก็ได้ เปล่าไฟล์วิดีโอผมใหญ่ด้วย อันนี้ครับไม่เป็นไรเดี๋ยวไม่โชว์ก็ได้ไม่โชว์ก็ได้เดี๋ยว The future, this is a research team, my student and a doctor from Signal University. And the second research is violet capsule image analysis. The problem for the motivation where this project come from. This project from a team from network company, and the problem is when the doctor when a patient has a problem of the gastrointestinal tract problem, they have to check the inside the body by using a violet capsule, and it take many image and basic. Actually, there are many diseases in that can analyze from capsule image, but the basic one that we can implement first is breathing region segmentation. This is a most common problem that can see from the image. We our objective to help the physician. Normally they have to spend 40 or 90 minutes to analyze the image by their eye, and we want to check which image has the abnormal disease, abnormal condition by using computer. But in this research, we use a deep neural network, but this network not quite appropriate for this problem. The accuracy is not so high. The left side is input data, and in this right side is our segmentation result that have both incorrect and correct result. And this is our research team for this project. This is all of my research and how to apply computer in my research.
Okay. Thank you very much, Professor Tikapan, for your presentation. So next, I would like to introduce Assistant Professor Trevor E. Carlson from National University of Singapore for a presentation. Please welcome.
Screen. Okay, good morning, everyone. We had a little bit of rain, but I think things are clearing up. I hope everyone's doing okay this morning. So my name is Trevor Carlson. Who am I? I'm an assistant professor at the National University of Singapore. So I've been there only for 4 or 5 years now, not very long. And so I'm sorry for the font. It seems weird. But anyway, I haven't been there for very long, but I've been trying to do some fun things in something called computer architecture, which is a way to make systems more efficient and faster and while maintaining programmability. So the topics that we look at are high performance edge computing. We look at trying to build server processors that are quite efficient. We also do a lot in something called simulation and analytical modeling. I've been working recently, maybe in the last 2 or 3 years, on security. So side channel security, you might have heard of Spectre and Meltdown. We're also doing EM security or power security, where you can listen in on a processor and sort of get the secret key. We're also doing something called software security. I'm not going to talk about all these topics today. But we're also building accelerators, AI accelerators, graph accelerators, and things like that. So what I thought that maybe we'd have some more undergraduates here today. So I'm going to skip kind of my my view on the stages of research, which is, you know, starting with some innovation and engineering and moving into innovation and finally research, right? And so, but well, I'll talk a little bit more. I'll just skip this for now. One thing I wanted to do before I talk a little bit about my research is talk about one of the things that we're trying to do here with NUS, which is we're trying to build a workshop at end of October, the beginning of October, where we can bring the top undergraduates from Thailand to Phuket, where we can put together a computer science research workshop targeted to helping undergrads understand what is research, what can you do with this, and how can you become potentially a PhD student or master's student, things like that. Basically, the goals are to help those students understand what computer science research is, get those students interested, allow for interaction, fun things like that. And right now, NUS is planning on covering the housing costs for students, the best students, to come here, and then we can. So the goal is to work together with the different universities here so that we can do this. Okay, that's just a quick aside. So back to a little bit of the research that I've been doing. So the goal is to build basically something like this, right? You know, bees do a really great job of pulling together lots of different workers. They work autonomously, they work independently. Wouldn't it be cool if our CPUs and our processors could do something like that, right? We're also moving more and more towards this distributed edge compute. So now another question is, well, we want to have high performance edge processors. How do we build those so that they can do everything that our mobile phone can do, but with a much smaller form factor, much smaller energy consumption? We'll just go back here. So one of the questions that I really want to do is, you know, when we look at traditional CPUs, and we heard about this earlier, where CPUs, they want to buy the latest CPUs, buy the latest servers, and people using more and more, they're using GPUs. What we're trying to do is create a new type of processor that can be flexible and fast and get the speed of a GPU, but with the programmability of a CPU. So that's kind of the thing that we're doing in our lab. One of the big things is efficiency. We don't want our, we don't want to lose our environment, right? So we need to make sure that we're efficient when we build our systems, such that the solutions that we create are, what's the word? You know, we're providing a more efficient world. This is not a platform that I built. This was a platform for NUS. The idea was when you start building these IoT devices, these edge devices, you want to put more and more compute in these things. So this is a monitor. You drop this swan into a pond, and it will watch for. It'll check the water quality. It'll check for pollutants. It'll check for chemicals, and it sort of just wanders around. And it's kind of nice, right? You get this design that's pleasing. Right? You don't mind watching a little swan around, you know, going around but you also get the technology. Maybe you can get, you know, the kind of things that we would like to do is augment something like this and add automatic mapping using AI to do some maybe image analysis on the state of the pond or the state of the reservoir, things like that. Okay, so what's been happening recently is that a lot of people in computer architecture, which is what I do, they've been looking at things like Dennard scaling and Moore's law, which means that technology scaling really isn't doing what it used to. It's not giving us more and more transistors at lower cost. So now we have to do more with less, and that's kind of what our group is trying to do. But that's really a big challenge. So how do you do that? One of the ways we do that is we try to do new things with software and hardware. It's called hardware-software co-design. So basically, this little diagram on the lower right, you can see transistor costs is starting going up. Right before, everyone's like, "Oh, processors are cheaper, getting cheaper and cheaper." But this is not. This was pre-inflationary days, right? This was already happening. Prices going up, right? So today it's going to be even worse. And so now what happens? We built a little processor. The diagram is there, but the point is that it's both energy efficient and area efficient, which means that it's really affordable to drop one of these into your devices. So what kinds of things do we do? So we build simulators. We predict future processor performance using today's processors. That's what we do. That's one of the things that we do. We also build analytical models and something called sampled simulation. Imagine your simulator is 10,000 times slower than real world. How are you going to actually simulate a real processor if it's 10,000 times slower? You can't. You don't have years and years to wait. So you need to build a smaller version of the program that still accurately represents that machine. So that's what we do. We also build lots of fun processors. I'm just showing 4 or 5 of the ideas that we've had recently. These are processors that help those small devices get faster. This is also processors that help the big devices become more efficient. So I just wanted to talk a little bit about one of our recent papers at HPCA 2022, which was, it's a logarithmic scale on the upper right-hand corner, but let's just say smaller is better. Runtime, when you have a bar on the upper right, if it's closer to the bottom, that means that it only takes a day, not a year. And so previous techniques are all the way on the top, the red bars really high. And so what we've been able to do is this red dotted line is showing now we can, instead of simulating for a year, we can simulate for a day. And we can give you the same accuracy. And that means you could design your new processor in a way that says, okay, I'm pretty accurate that the results that I've just simulated are good and representative. I'll skip kind of some of these things in the interest of time. But overall, what we do is we look at an application on the left. You see this code, right? All applications are made of lots of loops. And then we look at the application and we split it up into different regions. And then it turns out that there are patterns inside the code. And by analyzing the patterns, we can automatically build up a system that can speed up the simulation. I'm not going to go into all the details, but in fact, you get around a 31,000 times speed up on this simulation time. So what that means is now you can extrapolate or understand what the performance is of your system without actually doing the entire application. So that's really cool. One other thing, I just wanted to give a quick overview. I got about a minute and a half about the one of our latest CPUs. This was accepted to ASPLOS 2021. And the idea here was that processors today, they are speculative and they try to do a lot of work. But it turns out that they have very limited resources internally and they hold on to those resources a lot longer than normal. So the problem is if you only have like, let's say 1,000 items, if you're holding on to half of them, you can't use them for other work. So what our insight was is that maybe we can get rid of these things and push them out of the processor earlier than everyone else does and use that free space to do more useful work. So I'm not going to go into all the details. Basically, we build a CPU, we augment the CPU with all of these new structures. And the key is that we use software to annotate the system, and we give the hardware permission to do more. In the end, I'm not going to go into all these details, but in the end, you get something like an 18% to 26% performance improvement, which is significant because if you think at what Intel and Apple do generation after generation, each little enhancement tends to be, or ARM in this case, each little enhancement tends to give just a few percent, right? So this 20% is not bad. I'm not going to talk about, oh yeah, and this is my last slide, right on time. Thank you, everyone. If you have any questions about the workshop coming up in October or any of our research work, please feel free to let me know and have a great day. Thank you.
Okay, thank you very much, Professor Carlson, for an exciting and interesting talk. Okay, next, the last one will be the presentation from Professor Dr. Kiyota Hashimoto from Songkla University.
Okay, good morning, and I try my best not to reduce the lunchtime. Okay, so yeah. Okay, so how computer will change the life. And my name is Kyoto Hashimoto, and I'm working here, Faculty of Technology and Environment. And my expertise is the data science as well as an AI, machine learning, and natural language processing. Okay, so anyway, computing has already changed the research, right? So we have a big data, or analytical methods are also changing, and also result presentation is also changing. For example, long time ago, the representative value is some sort of an average or something. Now we have a lot of maps and other things, so the result presentation is also changes. And also, thanks to the researcher like Trevor, speed is also going up. So calculation speed and so a greedy approach can be done, and all those kind of things. So computing has already changed the research. And then nowadays, I'm making a lot of collaboration with a scientist, not the computer scientist, not the data scientist, the environmental scientist or geophysical scientist. And then we found that there's a lot of difference or sometimes a conflict between the traditional science and data science. Okay, science basically emphasizes description. So more static or deterministic in a sense. And many topics in science pursue the description of the present or past reality, not the future. And the pursuit of precise, accurate description, and the pursuit of the simplest rules behind description. So if something can be done, can be written as the A plus B, that's the best for them. Okay. And of course, the explainability matters. On the other hand, how about us? Maybe some of you are the same with me, data scientists or something. Okay, then our approach is more dynamic and probabilistic. And many topics in data science pursue predictions. And also, we emphasize our models can be applied to different situations or something, which means that the pursuit of robust approximation or adaptability. And of course, an acceptance of complexity and complications, and basically result matters. So many of the paper boast that, our experiment shows that our methodology improves 1% of the accuracy or something like that. This is the result, not the explainability. So there's a lot of differences. Okay. Based on this idea, basically, I think that the issues and future of data science can be divided into 3 phases: core, methods and techniques, and applications. And then what is core? Actually, not so many people are aware of it, but why we are saying data science? Data science means that the science of data, right? So very foundational question is, what is the nature of data themselves? So any crucial characteristics or patterns of different kinds of data, or any significant characteristics consider data a study target, not about the data of something, data itself. And also the second one, methods and technique, what are more resultful methods and techniques, which is the main part of a research usually. And more and more advanced machine learning needs a lot of computing powers and money for electricity. And also the applications, how data science apply to scientific questions. So the last part is what I'm doing now, that we are making a lot of collaboration with environmental scientists, geophysicians, or some other people to apply our methods to them. But then there's always an endless discussion. Why are you doing that? Oh, I want this kind of things. Oh, I need interpretation or something like that. So one of my suggestions for the future research is we should have more collaboration, not only within the data science or computing, but also within different areas. So which means the interdisciplinary or transdisciplinary. But then we have to be aware that the different people think differently, very simply. And we have to accept what they think is important. And also we can explain what we think important. So there are more communication is more necessary. So prospective collaboration between science and data science, okay, based on big data, many features, less interpretability, heuristic search, predictive approach. This is on our side. And then, of course, we can use a lot of sensors, particularly for IoT, and also the heuristic discovery of a new combination like genomics and other things. So it is more like a mining approach. And also using the image processing is now everywhere for the climate prediction and all the other kind of things, and the geoinformatics and genome informatics. So you already know that we are saying geoinformatics, genome informatics. So some blah 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 informatics. This is a combination of the science and data science. But then most of the cases, explainability and interpretability matters, which is not so good for data science. Okay, now I'm talking a little bit about my recent research. The first one is crowd sizing with Wi-Fi. So we use Wi-Fi to detect how many people there are in some area. Actually, we are not using surveillance camera that another lecturer, another teacher said, because it is a little bit more difficult and there's some sort of political issues. So we are using a beacon and sensor, and then there are a lot of related research. But what we did is very simple one. So we set some sensors in classrooms, and we checked how many people there are in classroom A or classroom B from what time to what time. And of course, this is signal processing matters, but then we improved some of the result by using some machine learning techniques. So this is some sort of collaboration between in this case, environmental scientists and data scientists. And also, we changed Wi-Fi into Bluetooth, because the Bluetooth is more appropriate for shorter range. And then, in this case, we made some social experiment in an international conference, which gathered 400 people, and we can make the person's trajectory like this one, or even a little bit more dynamically. Okay, now the room A has more people, room B has more people. Okay, we can make some sort of announcement there or some. And also from a little bit different part, of course, you know that Phuket has several coral colonies around, and now most of them are in danger of contamination and pollution. And so we are now using an image classification technique to know how much of the coral are still okay, still active, and how much of them are in danger. So like this way, so the left side is a picture that the diver took in the sea. And there we make a machine learning technique to point out the blue part is still active. Blue part is now in danger. The other part is still alive. Okay, so anyway, data scientific approach is indeed useful for many scientific fields. Maybe much better than we data scientists or computer scientists recognize. Indeed, many scientists come to talk to me that, oh, we want to make a collaboration to use some data scientific techniques. But then after talking 10 minutes or so, we find that, oh, what they want is a little bit different from what we know or something. So collaboration between science and data science needs a lot of communication. And then lastly, why data scientific technique is often not explainable is the character of non-linearity of machine learning techniques. So usually non-linearity needs a lot of non-explainable part. So thinking, recognizing this, now maybe you know that XAI, explainable AI, and other sort of direction of the research on interpretability of a machine learning technique is going on. So this is also a fruitful area to boost up the collaboration between science and data science and other areas. Okay, thank you.
Thank you very much. I think everybody's hungry now, and it's lunchtime. The lunch will be served on the 6th floor of this building, right? So we're gonna follow Dr. Dr. Penนะคะ. Okay, thank you so much. And I'll see you here. What time? Say again. 1:30 for the discussion panel. Thank you very much. See ya.